Most folks in this audience realize the importance of metabolite ID. The guidance expects that we essentially assign and show what the major metabolites are circulating from a metabolites and safety testing standpoint. You want to make sure that your tox species generate these metabolites to sufficient levels so you have coverage and safety coverage. We also want to know what the major circulating metabolites are that may be cause drug-drug interactions, may be pharmacologically active, so this is obviously important. And we also want to be able to show what enzymes might be involved in generating these metabolites. So prior to phase 1 dosing, we really rely on in vitro systems for this, for the reasons I just outlined. But again, for low clearance compounds, these conventional systems, microsomes and suspended hepatocytes, really have become inadequate, not just for generating metabolites, but also doing cross-species comparisons. So a study that we very recently conducted, we have some data that I'm going to show you that's really about 2 weeks old, where we compared turnover and metabolite profile in a 4-hour suspension. We did just human only at this point, compared to a Hurel model and a 24-well plate design, where we did a time course 4 hours, 24 hours, 72 hours, and 7-day incubations, continuous incubation, no media change. We chose several compounds, 3 of which I'm going to show you: meloxicam, timolol, and this XK469, which is not something that most people might be familiar with, but this is a very, very low turnover substrate for aldehyde oxidase, which is one of my interests. And incubated at 10 micromolar, and then basically did analysis using high resolution mass spectrometry, a thermo-orbitrap instrument, and we compared the metabolite profiles. So here's the first one. This is meloxicam. Metabolism, the structure is shown up here. We know that one of the main sites of metabolism is hydroxylation at this position here. And what you will notice in this panel, this is the panel of several chromatograms, is that this is the chromatogram for the following a standard 4-hour incubation in suspension. And then as you go down, you see the Hurel 4-hour, 24-hour, 72, and 7-day incubations. And what you will see is, while you can see some of this hydroxylation, very low level, and this is normalized to parent peak area on this side here, you see a very low level metabolite. But in the Hurel system, what you can see is that this metabolite actually does grow as you go down. And by the time you get down to about 72 hours at 168, what you actually see, it's hard to visualize, but the hydroxyl metabolite actually starts to decrease in intensity while the secondary carboxylic acid starts to come up over time. So by the end, you see carboxylic acid in the middle here. And what's really interesting is you compare this to the published in vivo data following the C14 ADME study. The carboxylic acid represents about 60% of the dose. So it is the most prominent metabolite in vivo. And following a 4-hour suspension incubation, you would never have predicted that. Secondly, here's timolol metabolism. Timolol seems to be metabolized primarily on, see if my laser pointer is going to work here. Let's do this one. That's better. Metabolized at this morpholine ring, shown here, to form some ring open metabolites, shown here and here. Again, comparing the same panel of different chromatograms, you can see an initial hydroxylation, which ultimately ends up in the Hurel model, progressing further on to what I'm going to highlight here is a morpholine ring opening metabolite, shown here, and loss of the ethyl bridge, one of these ethyl bridges here at this position, which again you don't see or only trace levels in the suspension. Okay, and again, these two metabolites appear to be prominent metabolites in vivo based on reported C14 ADME data. Another point that's really interesting is that you see formation of a direct glucuronide. You can see this glucuronide is growing with time. So not only do you have good P450 activity, you have good UGT activity sustained out for 7 days as this metabolite appears to continue to grow. Okay, so some good phase 2 metabolism as well. Lastly, this XK469 compound. So here's the structure here, and what we know about this substrate is it's a very, very low turnover substrate for aldehyde oxidase. When we incubate this compound in a 4-hour suspension, you do not measure any metabolism. You don't see clearance based on depletion. And certainly with this chromatogram, you can see little to nothing is occurring. Yet in the Hurel model over time, what you can see is here's the hydroxyl metabolite highlighted in red. This is generated by aldehyde oxidase. You can see that it's still growing over time. So in vivo, again, as reported from literature, this is the most predominant metabolite. In addition, we also see glycine and taurine conjugates. These are pretty rare to see in vivo, but were actually also reported in this in vivo study. Turns out they didn't represent a large percent of the radioactivity in the urine. And again, the aldehyd oxidase metabolite was the most prominent. And so this is really important because aldehyd oxidase, if you don't know, there's very profound species differences. Dog actually does not express active aldehyd oxidase, and in general, rat is very low activity relative to human. So not only would you not have seen this metabolite in vitro in its suspension, but you also would not have identified a potential species difference and a lack of coverage for this particular metabolite for human safety. So this is very critical.